Guys, welcome to another round of chemistry notes. In this video, we are going to talk about quantum numbers. So quantum numbers are a little bit like what we were doing in the other videos, our other types of notations, but they are talking about one specific electron. So orbital notation and standard electron configuration and noble gas configuration, those all talk about all of the electrons. Here are all of the electrons in this element, in this atom. Quantum numbers focus on one specific electron at a time. And there are 4 quantum numbers that help us narrow it down where that one electron is. We start out really general and then we bring it in really narrow. Your first quantum number is the most general, the most sort of vague, broad quantum number. That is the principal quantum number, and we represent it with the letter n. Always a lowercase n, never a capital one. So your principal quantum number, n, indicates the main energy level. Remember, the numbers of your main energy levels are the same as the numbers of the rows, right? So your first main energy level is the first row in your table. Your second main energy level is your second row in the table. Third main energy level, 4th, 5th, 6th, and 7th. But do remember there are some exceptions to that, right? Your d orbitals are a little weird. So while this is your 4s, this is your 4p, this is actually 3d here in the middle. So while, yes, right here, n equals 4, and right here, yes, n equals 4, right here, n equals 3. So n can be any positive integer, so 1, 2, 3, 4, 5, 6, 7, those are the ones we know about right now. There has been some evidence of elements found in n equals 8, but none of those have been proven. Theoretically possible, just not a thing yet. So in this class we talk about n equals 1 through n equals 7, and the n is just the number of the subshell. So if you're looking at your 4f subshell, that would be n equals 4. If you're looking at anything in the second row of your table, that's all n equals 2. Just whatever the number is, that's your main energy level. Your second quantum number is the angular momentum quantum number, and we represent that with an L. Specifically, a cursive L, right? Because if we drew it just like a regular lowercase l, it would look like a 1, and that gets confusing. So we tend to draw it as a cursive L, so it's really clear that's what it is. And that indicates the shape of the orbital. Values of L can be from 0 all the way up to n minus 1. And the values of L go in the same order as the orbital shapes we've already learned. So your lowest value of L, which is 0, is your lowest energy orbital. That's your s orbital. If L has a value of 1, that is your p orbital. If L has a value of 2, that is a d orbital. And if L has a value of 3, that is an f orbital. If you have n equals like 6, then you could technically have an L value all the way up to 6 minus 1, which is 5. So we could have values of L that are 4, 5, 6 even. We don't have orbitals that go with those, but if you ever see something like 4g or 5h, the orbitals just kind of keep going. You don't need to know this, just in case you were curious, because according to this n minus 1, our L values could keep going. They don't have to stop at 3. They just do because we've only discovered orbitals in these 4 shapes as of right now. Your most common values of L, 0, 1, 2, 3, because your orbital shapes that we know of are s, p, d, and f. All right, your third quantum number. So far we've said, all right, here's the energy level we're in. Here's specifically the orbital we're in. So the first 2 quantum numbers together give you your subshell. You could say, oh, I'm in the 4s subshell. Or you could say, oh, n equals 4 and L equals 0. These 2 things mean the exact same. They're just telling you where on the table which subshell is my electron in. Your next quantum number is going to tell you specifically which orbital within that subshell. So your third quantum number is your magnetic quantum number, and we call this m sub L. And again, we use that cursive L so it doesn't look like a 1. This indicates the orientation of an orbital around the nucleus, which is the same as saying, oh, it's this specific orbital. And it can have values of negative L through 0 all the way to positive L. So here we're looking at our p orbitals here. The L value for a p orbital is 1. Always, if it's a p orbital, L is 1. So remember, S is 0, P 1, D is 2, F is 3. So p orbitals, L equals 1. That means the possible values for m sub L are negative 1 through 0 to positive 1. So this is our negative 1 orbital, this is our 0 orbital, and this is our positive 1 orbital. So we narrow it down even farther. So again, just to review what our quantum numbers have told us so far, we have our periodic table with our different blocks, and our different rows, saying that I have n equals 3 tells me that I am either in a 3s, in a 3p, or in a 3d orbital. That's what this tells me. Going on to my next quantum number, I said n equals 3 and L equals 1. Those two together tell me it has to be specifically in a 3p orbital. So that narrows it down a little bit. So adding this in there narrows it down to just right here on the table. And then if I add my magnetic quantum number, because remember there are 3 orbitals here, right? Orbital, orbital, orbital. Adding my magnetic quantum number and saying m sub L equals negative 1, that is telling me specifically it's not in this orbital and it's not in this orbital. It's one of these 2 electrons right here. So I've narrowed it down to, could have been 18 electrons, knowing just this. Adding this narrowed it down to 6. Adding this has narrowed it down to 2. And now I'm going to narrow it down to one single specific electron, and I'm going to do that with the spin quantum number. And that is m sub s for spin. It indicates the spin of an electron. Because electrons can only spin up or spin down, our spin quantum numbers can only have values of positive 1/2 for spin up or negative 1/2 for spin down. So when you add in this last quantum number, this 4th quantum number, that narrows it down to a single specific unique electron. Because remember, way back to the first day of this unit, remember the Pauli exclusion principle? The Pauli exclusion principle states that no 2 electrons can have the same set of quantum numbers. Because if they had the exact same 4 quantum numbers, they would be acting like the same electron. Remember that electrons are not identity thieves. So your electrons can have 3 of the same quantum numbers, that is fine, but they cannot have all 4 the same, because then they are in the same place at the same time acting the same way, and electrons don't full-on copy each other. So let's look at actually practicing our quantum numbers here. Look at our friend nitrogen with its 7 electrons. We're going to write our quantum numbers for each electron. So since there are 1, 2, 3, 4, 5, 6, 7 electrons, we are going to write 1, 2, 3, 4, 5, 6, 7 sets of quantum numbers. Let's look at our first electron here. We can color code them, sort of make it easier to read here. So this first electron here, we are going to write in this first column of blanks. This electron is in a 1s orbital. So that means its n value is 1, because 1. And its L value is 0, because of this s. S orbitals have an L value of 0, always. The m sub L value, remember, tells you which specific orbital. Again, this is energy level. L tells you the orbital shape. M sub L tells you specifically which one, which orbital, and then M sub S tells you which electron, the up one or the down one. And your M sub L values, recall, M sub L can have values from negative L to positive L. Well, our L value here is 0, so the only possible M sub L value is also 0. And then our M sub S value, because this electron is spinning up, is a positive 1/2. So the quantum numbers for this specific electron, we say n equals 1, tells us we're in the first energy level. L equals 0 tells us we are in the first type of orbital, tells us we are in an s orbital. M sub L for your s orbitals is a little redundant. It'll make more sense when we look at our p orbitals. But M sub L for an s orbital is always 0. And it's spinning up, so it's got a positive 1/2. Looking at our next electron over, this second electron, it's going to look largely the same because they share pretty much everything, right? This electron here, they're in the same orbital, so they're in the same energy level, n equals 1. They're in the same shape orbital, L equals 0, s orbital. They are in the same exact orbital, the 0 orbital, but this one spins down. So it's got a negative 1/2 spin. So again, this is your Pauli exclusion principle at work. This is the reason that this one has to point down, because if our second electron here pointed up, then it would have 1, 0, 0, and plus 1/2 as its quantum numbers. It would be an exact copy, and that's not okay. So that's why it has to spin down. This is not a thing it can do. All right, so those are our first two. Let's look at our third one. Here's our third electron here. Now we are in the second energy level, the 2s. So n equals 2. It is still an s orbital, so L still equals 0. Because it's an s orbital, the only M sub L value is also 0. And this electron is spinning up, so plus 1/2. This fourth one here. We are still in the second energy level, so n equals 2. L equals 0 for that s orbital. M sub L equals 0 for that s orbital, but now it is spinning down, so negative 1/2. Your s orbitals are always going to look pretty similar to each other because the only M sub L value is 0. The p orbitals are where it gets a little different. So let's look at our p electrons here. Let's look at this guy here. So now we are in the 2p orbitals. N is equal to 2. Because it's a p orbital, L is equal to 1. M sub L for our p orbitals could be negative 1, could be 0, or could be positive 1. So we just number those orbitals, these three things. You can put 0 in the middle, negative 1 to the left, positive 1 to the right. So this electron here is in the negative 1 orbital. And it is pointed up, so it's going to have a positive 1/2 spin. That's electron number 5. Let's look at electron number 6. All right, electron number 6 there is 1 orbital over, still in the second energy level, so a 2. Still in a p orbital, so 1 for our L value. But now it's in this center orbital, so its M sub L value is going to be 0 now. We've changed to a different orbital, so we get a different M sub L value. And it's still spinning up, so we've got a positive 1/2 right there. And then, last but not least, number 7. Our last electron here, still in our second energy level, so n equals 2. Still in a p orbital, so L equals 1. But now we're in a new orbital. We're in the plus 1 orbital, so M sub L is equal to plus 1. And spinning up, so our spin is plus 1/2. So that is how you write your quantum numbers. Sometimes it'll say, here is this electron, write your quantum numbers. Sometimes it'll say write the quantum number for the last electron into beryllium. In this case, write the quantum numbers for the last electron into nitrogen. In that case, you would only have to write this set right here, the identifying electron, the 7th electron. So sometimes you'll be asked to write all of them, sometimes it'll be specific. Write the quantum numbers for the valence electrons, write the quantum numbers for the last electron. It just depends on what you're being asked. You won't always have to write every set of quantum numbers for every single electron. Just depends. Read your question. So let's look at our next one here. Our next example says, consider a neutral atom of carbon-12. Question A says, write out the orbital electron configuration, also known as orbital notation, for the ground state of this isotope. Well, let's go ahead and do that first. Remember, carbon, even carbon-12, this is just specifying the mass. Any atom of carbon ever has 6 protons, because it's atomic number 6. And since we haven't learned anything different yet, that's also going to have 6 electrons. So we need to draw 6 arrows. Remember, our orbital electron configuration means draw all the lines, draw all the arrows. So we'll draw our orbitals. Number 1 is 1s. Number 2 is 2s. And then our third subshell is 2p. So 1, 2, 3 of our 2p orbitals. And then we can go draw in our 6 electrons. 1, 2, 3, 4, 5, 6. Go ahead, double check yourself. Go find the 2p block of your periodic table and make sure that the second element there is carbon. And if you look on your table, find your 2p block over on the right-hand side with your 1, 2, 3, 4, 5, 6 elements. This is carbon right here. It's the second one in, so that means we've done a good job. Letter B says, how many electrons in the ground state of carbon have quantum numbers n equals 1 and m sub s equals positive 1/2? We're going to circle the relevant electrons. N equals 1 means the first energy level. So here's n equals 1. There's only one orbital with n equals 1. And m sub s equals positive 1/2 means spinning up. So the only electron that is spinning up in our first energy level is this guy right here. So there's exactly one electron that has those quantum numbers. And letter C says, write a set of quantum numbers for each valence electron of this isotope. Well, carbon should have 4 valence electrons. In this case, they're the ones in the second energy level, right? So we have 2s and 2p. Within our second energy level, there's 1, 2, 3, 4 electrons. So that all checks out. We're going to have to write 4 sets of quantum numbers. I'm going to color code this to make it a little bit easier. We'll look at this guy right here first. And you don't actually have to put n equals, l equals, m sub l equals. They always go n, and then l, and then m sub l, and then m sub s. So you can just write out your 4 numbers and it will be assumed that is the order you are using. All right, so for this electron right here in red, our n value is going to be 2 because we're in the second energy level. And in fact, since we're doing this for valence electrons, they should all have the same n value. They're all going to start with a 2. So this electron here has n equals 2. It is in an s orbital. So it's going to have L equals 0. The only acceptable m sub L value for an s orbital is 0. And it is spinning up. So we'll have a positive 1/2. That's our first set of quantum numbers. Looking at our next one, we'll look at this guy right here. We are still in the second energy level. We are still in an s orbital. We are in the central s orbital, the only s orbital, the 0 s orbital. And now we are spinning down, so negative 1/2. When 2 electrons share an orbital, the only quantum number that will be different is the last one. The first 3 should all be the same if you're sharing an orbital. All right, let's look at our third electron. number 3 right here. We are still in the second energy level. Now we are in a p orbital, so L equals 1. And let's go ahead and number our p orbitals. 0 goes in the middle. That'll be our 0 orbital. Positive 1 goes to the right. Negative 1 goes to the left. So just a note, if you're ever doing this for d orbitals, which you are going to have to do, if you're looking at, I don't know, your 3d orbitals here, your 0 would go in the middle, negative 1, negative 2, positive 1, positive 2. Your orbitals are like a number line. 0 goes in the middle, more negative out to the left, more positive out to the right. So that is always how you can number your orbitals to help you out here. So our L value is 1 because this is a p orbital. Specifically, it's the negative 1 p orbital. It's the orbital to the left. So our m sub L value is the negative 1. And this electron is spinning up. So it'll be a positive 1/2. And that's your third electron. Number 4 is in the second energy level. It is in a p orbital, but it's in the 0 orbital. It's in the central orbital. And it is spinning up, so it has a positive 1/2. So at this point in your book, you've got several different types of practice problems. You've got some that are asking you to do what we just did, draw the orbital notation, identify which electrons have which quantum numbers, and then draw some quantum numbers for your valence. Go ahead and work through problems 1 through 3 that sort of follow the same order we just did. And then at the bottom of the page, you've got some more of those boxes that we saw before with our different notations. And now you're going to fill in the orbital notation, the standard electron configuration, the noble gas configuration, and the quantum numbers for the last electron for those 2 elements. So go ahead and do that practice. Check your answer over on my website and get to work on your quest, because now you know everything that is in that first quest assignment. Good luck and happy studying!